Hey folks, in this video, we're going to talk about something that you are going to use a lot when there's anything rotating or rolling, and that is called the parallel axis theorem. So in the previous material, we talked about determining the moment of inertia of an object, and as a quick reminder, in a linear system, mass is resistance to acceleration. Moment of inertia is resistance to angular acceleration. The differences are for mass, you don't normally have to calculate it. For moment of inertia, you usually do. So it's like an extra step in a lot of our problems. In the previous discussion, we were able to determine the moment of inertia of a rod or meter stick spinning about its center, that's your 1/12 ml squared, and about its end, it's 1/3 ml squared. There's a table of common moments of inertias of common shapes in your textbook in Giancoli chapter 10. You can also look them up online. There's all kinds of common shapes, a sphere, a cylinder, and other common shapes you might see, a hoop that has a dimension to it, etc. So what we're going to talk about today is a convenient way, if you know a moment of inertia of an object about its center of mass, of determining the moment of inertia from about any other point. So for instance, in these two examples here, let's say I'd had that rod and let's say you pinned it, I don't know, somewhere there and wanted to spin it about that axis. What's that moment of inertia? Okay, so you could integrate as we've been doing, but this parallel axis theorem is exceptionally convenient in order to figure out the moment of inertia about a point. It relies on knowing the moment of inertia of the object about the center of mass. So, for example, well, first of all, what's the equation? Let me tell you that. So the moment of inertia about any axis, so I'll put an x there, and we'll call this x. That's the axis you're picking to spin the object around, is equal to the moment of inertia of the object about its center of mass plus the mass of the object times the distance from the center of mass to the axis squared. And it's a really simple formula, but it's something that you are going to use a lot in the rest of the time in this course. So anything rotating or rolling, you're gonna be using this quite often. Okay, so let's do this example that I just drew right here. Now we have to come up with a fraction here. Let's say uh, let's actually start with this. Let's show you how this works with these two. So if I didn't know the moment of inertia of that rod about its end, okay, but I did know its moment of inertia about its center, it's a 1/12 ml squared, could I get that 1/3 ml squared? Sure. So I about the end of the rod is equal to the moment of inertia of the center mass, which is our 1/12 ml squared, plus m. Now, what you have to figure out is what's the distance from the center of mass to the axis you're interested in spinning the object about. In this example, if we're looking at the end of the rod, it's 1/2 L. Okay, and then you got to square that. So you get a 12th ml squared. I'll leave the ml squared for a minute, and then plus a quarter, and then ml squared. And a 12 plus a quarter is a third ml squared. So that's just an example of how to use this. Now let's say we're looking at the other one I drew. So let's say here's our axis. And just for fun, let's say that's 1/3 the length from the end of the rod. Okay, what's the moment of inertia about that point? So first of all, hopefully you're going to understand it's going to be somewhere between a third and a 12th ml squared because we're putting the axis between the center and the end. So our answer should be between those two fractions somewhere. So if we use our parallel axis theorem, I about that axis is what I of the center of mass, which is 1/12 ml squared plus m. Now here's the hard part about this parallel axis theorem. What's the distance from our axis to the center of mass? Well, this whole thing is 1/2 L from the end to the center of mass. We need to do a half minus a third, which is a sixth. So this is a sixth L. So that's what you're going to put here. You put L over 6, and then you square it. And you get a 12th plus 1/36th, ml squared, which is 4/30, which is 1/9 ml squared. So that, again, that's a measure of how hard it is to spin the object or to change its motion about that point. Okay. Another example, which would be very similar, is let's say you have your rod, and let's say you do this. Let's say you attach a very light rod to it. So we're not going to worry about the mass of that rod, and we'll say that has a length d. Okay, and you're going to spin this thing like this, like a big square lollipop or something. What's the moment of inertia now of this object? So this equation is really easy to use. You say, okay, well, the moment of inertia of the rod about the center of mass is 1/12 ml squared plus m, and then what's the distance from our axis to the center of mass? Well, just d squared, and that's pretty much all you do. You can't simplify that much more than that unless I give you numbers for L and D. So that's another example. Another example I'll do with you guys is, let's say you have a cylinder. Okay, any disk or cylinder has a moment of inertia of about the center of mass of 1/2 mr squared. Okay, so if you were to run an axis and spin this thing like a roll of toilet paper about that axis, its moment of inertia would be 1/2 mr squared. Okay, well, what if instead you choose to spin it about its edge? Okay, so it's like a toy now, and it's spinning like that around that axis on its edge. So we'll call that axis A. So the moment of inertia about axis A is the moment of inertia about the center of mass of the cylinder, which is still your 1/2 mr squared, plus m. What's the distance from the center of mass to our new axis? Well, it's just r in this case, and you got to square that, and this becomes 3/2 mr squared. So spinning it about axis A would be 3 times harder than spinning it about the center of mass. Okay, and furthermore, what if you had something like this? What if you had the cylinder, and I'll draw it a little skinnier now, but by the way, the height of the cylinder doesn't matter. All that matters is the radius and the mass. And let's say you attach a rod to it, so now it's like a lollipop. And this has a radius r, and the lollipop handle has a radius or a distance, let's say L, and you're spinning it about the edge. Okay, so why you would spin a lollipop, I don't know, but we're going to try it out. So we'll call this axis C. All right. What's the moment of inertia about that axis? Okay. So imagine you're spinning it like right now, it's coming out of the page at you. Okay. So that moment of inertia about point C there is moment of inertia of the cylinder, which is 1/2 mr squared, that's center of mass, okay, plus m times, now what's the distance from the center of mass to the edge of the handle? Well, that is L plus r, and then you would square that. And if you want, you could get like terms there. You could FOIL out the right-hand side. But for purposes of this discussion, we don't need to do all that. That's how you would calculate the moment of inertia of that object. So it turns out, again, if you know the moment of inertia of any object about its center of mass, you can calculate the moment of inertia about any other axis you want to spin it around by using this thing called the parallel axis theorem. This is incredibly important to remember. You're going to be using it a lot in the next month or two, and you're going to see it, you almost invariably see it on an AP exam at some point. So I hope that was helpful, and thank you very much.